Hello, everybody. Welcome back. So let's continue our lecture series. Um, Today we are going to continue studying about the reactions mechanisms. So I will show you some factors that influence the kinetics and the thermodynamics of reactions, and hopefully we will have time to discuss all the points. So let's start here sharing the screen. We move on to the PowerPoint. Okay, so that was the point that we stopped last time. So as I told you, we are going to study today the factors that influence the inorganic reactions, okay? So remember that we are focused here in the substitution reactions. So that's a general scheme for an inorganic substitution reaction. So we are going to add up Y to the coordination sphere and kick out L. And as we saw last time, we can have three different ways to do that: by association, dissociation, or interchange. And we discuss in details each of the mechanisms. So today we are going to focus in the factors that influence the kinetics and thermodynamics. So we have three major factors. First one is the size of the metal. Second one is the oxidation state. Third one is the chelate effect. And fourth is the energy of the intermediate, okay? So first and second factors, they are kind of the same, and third and fourth, they are very different, and they are more correlated with the thermodynamics of the system. So let's start with the first one, and that's size of the metal. Okay, so smaller ions have a stronger interaction with the ligand, resulting in shorter and stronger metal to ligand bonds, reflecting in slower kinetics. So imagine this system being the metal as a positive charge and the ligand as a negative charge. So there is electrostatic interaction between the two. So if we have a small ion, the ligand can get closer. So that shortens the chemical bond and strengthens the bond. So it's hard for the ligand to leave and insert uh, the L ligand. So example of this factor is the water replacement in hexa-aquo strontium, calcium, and magnesium complexes. The fastest one is strontium, intermediate is calcium, and slowest is the magnesium. And as we can see here, the largest ion is strontium 2 plus, and the smallest one is magnesium. Okay, so size, decrease the size, slow kinetics because the stronger interaction. And that's basically the same principle that we have for the oxidation state. Very similar to the size effect. Higher oxidation state results in a stronger interaction with the ligand. Again, stronger bonds reflecting in slower kinetics. So again, let's use the electrostatic model. So higher oxidation state means a large positive charge, so that will attract more the ligand and strengthen the interaction metal to ligand. Therefore, it's hard to remove this ligand and replace with a L ligand. And that can be exemplified in the water placement in sodium complexes compared with magnesium and aluminum. So the fastest one is sodium, magnesium is the intermediate, and aluminum is the slowest. And as you can see here, sodium plus, magnesium 2 plus, and aluminum 3 plus. So that's the effect of the oxidation state on the kinetics. High oxidation state, slow kinetics because of the strong interaction metal ligand. Okay. All right. We covered the points, the first and second points. So let's move on now to the third point, which is the chelate effect. So at the beginning of the semester, I told you that ligands that form multidentate bonds result in stable metal complexes. And this stability is related to changes in entropy. So we are always looking for a variation of entropy or a change in entropy. And that's always the entropy of the products minus the entropy of the reagents. Remember that entropy is a measurement of the disorganization of the system. Okay, so first thing, let's remember what is a multidentate ligand. So multidentate ligand by definition is a ligand that can coordinate to the metal through 2 or more atoms. Okay, if the ligand has 2 atoms that are capable of coordinating to the metal, that's called a bidentate ligand. 3 atoms, that's called a tridentate ligand. 4 atoms, that would be a tetradentate ligand, and etc., etc., etc. If we have a bidentate ligand where the 2 atoms are bonding to the same metal, that's called bidentate chelate. If each atom is bonding to a different metal, that's called bidentate bridge. Okay, so just a quick recap. So now let's understand why a chelate ligand enhances the stability of a complex, or why it's so hard to remove a chelate ligand. So first, let's understand entropy. So as I told you, entropy is a measurement of the disorganization of the system. So we can compare that with the number of people in a given space. So for example, this very sad party here, so that's very empty. So that's a low entropy party. And on the other side of the spectrum, you have here all the happy people here. So this is pretty crowded. It's a lot of people around. That's a high entropy party. Okay, so chemical systems, you can do the same analogy. If you have few atoms moving around, that's a low entropy state. And if you have a high number of atoms moving around, that's a high entropy state. And remember, everybody wants to be in a high entropy party. Okay, everybody wants to be in a high entropy party. And that's the same with chemical reactions. Reactions that increase the entropy, they are probably going to be spontaneous, okay? We are always looking for an increase of the entropy. So now let's take a look how the chelate effect enhances the entropy of a system. Okay, so let's consider a generic reaction here. We have a metal complex as a starting reagent, and that's going to react with a ligand that can coordinate through the Y atoms, so it doesn't matter what's that. And in this case is going to form a chelate, okay? So it's a bidentate chelate and replaces two L ligands. Okay, so now I want to analyze with you what happens with the entropy of the products compared with the entropy of the reagents. And remember, all the reactions want to move towards a high entropy party. And as I told you, the entropy is correlated with the number of molecules. So imagine that each molecule here is a person. So let's count the number of people in the beginning and the number of people or molecules at the end and compare beginning and end. So I'm going to represent by spheres. So we have here 1. So you're going to count the whole complex as one person, and the bidentate ligand that's not coordinated yet as a second person. So we have 2 people here. Now, at the end, we have 1 person here and 2 people here. So that's a total of 3 people. So as we can see here, we have at the beginning a party of 2 and at the end a party of 3. Therefore, there is an increase in the entropy from left to right. All the reactions want to be in a high entropy party. Therefore, the reaction is spontaneous from left to right. So that means when we inserted the chelate ligand in the coordination sphere, that is a spontaneous reaction. Therefore, the product is more stable than the reagents, and that's why the chelate enhances the stability because increases the entropy of the system. Okay? So now if we analyze the reaction from right to left, now we are forcing the chelate out and inserting the 2 ligands back, and would produce this kind of situation over here. So let's take a look at the entropy. So we have 3 people at the beginning and 2 at the end. Therefore, the entropy of the products from right to left is lower than the reagents. Therefore, nobody wants to go from a busy party to a empty party. Okay, so therefore, the reaction from right to left is non-spontaneous. Okay, so we saw the influence of size, oxidation state, and now the chelate effect on the inorganic reactions. Let's move on to the fourth point, which is the energy of the intermediate state. Energy plays an essential role in motivating a reaction to move forward or backward. The ligand field stabilization energy gives us an idea of how stable the intermediate is compared with the starting complex. Furthermore, using this approximation, we can predict if a metal complex is labile or inert, or if it's going to react or not. So one thing I want to make clear before we move on is that the ligand field stabilization energy that we are going to calculate here is a very rough approximation. However, it predicts correctly if a complex is labile or inert, or if it's going to react or not. So remember about the ligand field stabilization energy that's correlated with the splitting caused by the ligands in the coordination compound. So if we don't have any ligand, the 5d orbitals have the same energy here. However, when we place the ligands in an octahedral geometry, there will be a strong repulsion between the dz squared and the dx squared minus y squared orbitals with towards the ligand. So every time there is repulsion, there is an increase in the energy. So this group goes up and it's called EGE, all right? If someone goes up, someone else has to go down, and that's the T2G group, all right? So remember that. The T2G group is stabilized by minus 0.4 of the delta O, and the EG group is destabilized by 0.6 of the delta O. Important detail here. Electrons in the T2G orbitals are stabilized, while in the EG orbital are destabilized. Okay, so every time we add up electrons here, the system will go down in energy, and if we start to add electrons up here, the system will go up in energy. And again, what we are going to do here is a rough approximation of the energy of the system, okay? Just to make sense of labile and inert behaviors. Okay, moving on. All right, there are two possible ways for a substitution to happen: association or dissociation. So let's take a look at each of the possibilities and let's try to make sense of the energetics of the system. Okay, so here in the middle, we have the starting complex. So that's a octahedral complex with coordination number equals to 6. If the reaction goes through an association mechanism, one extra ligand is inserted in the coordination sphere, forming a 7-coordinate intermediate. And this is the geometry. Okay, so we have a pentagon here and 2 ligands in the axial position. Okay. On the other hand, if the reaction undergoes a dissociation mechanism or dissociative mechanism, the first step is to lose one of the ligands. Therefore, the intermediate formed has a coordination number equals to 5. Okay, and that's the coordination geometry. It's a square pyramid. Okay, 4 ligands in the plane and 1 axial ligand. And here we are going to not go deeply and analyze the effect of each ligand under each d orbital. So I will provide you a table, but that's how we should do. Okay, that's how it's done. So if you put the complex in a box and verify all the repulsions and the positions of the ligands, we are going to come up with something like that. Okay, so the middle one is the d orbital splitting for a 6-coordinate species that has a OH symmetry. So this here you know, right? T2G and EG, all right? So electrons in these orbitals are stable, and every time you move up, the system gets less stable. For a 7-coordinate species, the d orbital splitting will look like something like that. So we have here at the bottom dxz and dyz. And then up we have dxy, dx squared minus y squared, and dz squared right here. Okay, so for the 7-coordinate species, electrons in these 2 orbitals are stable, and every time you move up, the system gets less stable. And finally, for the 5-coordinate species, we have dxz and dyz at the bottom, followed by dxy, dz squared, and dx squared minus y squared. In this case, dxz, dyz, and dxy are below 0. Therefore, electrons in these 3 orbitals stabilize the system, while dz squared and dx squared minus y squared are above 0. Therefore, electrons going to these orbitals will destabilize the system. Okay? So what we are going to do is to basically count the electrons and place them in the adequate orbitals and see how much is the total energy of the system. And remember, for the system to go from octahedral to any of the other 2 geometries, there must be some sort of stabilization, right? So nobody wants to go from a stable state to an unstable state. Always the opposite, from an unstable to a stable, or from stable to more stable. And this stability or the energy of each system will be determined by the ligand field stabilization energy. And just for comparison here, the units of the energy are divided by 0.1 of the delta O, so we can compare the three different geometries. Okay, so now what I would like to do together with you is to analyze for each D configuration, D1, D2, D3, D4, D5, D6, 7, 8, 9, and 10. What's the energy of the OH geometry, the D5 age, and the C4V symmetries. And with that, we can decide, okay, so the system, if the system moves towards one of the geometries, it will get more stable. Therefore, the reaction happens. If the system moves towards a less stable state, the reaction will not happen. Okay, so at this point, I will stop the PowerPoint and move on to the paper because I want to do together with you. Okay, so I will stop the recording here and then add up a second video.